Hi guys, let's do number of provinces. So there's n cities, some of them are connected while some are not. If city A is connected directly with city B and city B is connected directly with city C, then city A is connected indirectly with city C. And they tell us that a province is a group of directly or indirectly connected cities and no other cities outside of the group. We're given an n by n matrix called is connected, where is connected at I at j equals 1 if the ith city and the jth city are directly connected and it equals 0 otherwise, and they want us to return the total number of provinces. So in this example, we would return 2, because basically we're just returning the total number of components in the graph. So since there's 2 components here, we'd return 2, because as we can see, nodes 1 and 2 are connected, and 3 is disconnected by itself, so we have a total of 2 separate components here. In example 2, we have a total of 3 separate components because none of these nodes are actually connected to each other, so we would return 3. So I've already gone ahead and copied and pasted our example 1 here for our is connected array so that we can look at this more easily. But since this is an array of edges basically, like because it's like demonstrating like what is connected to what, then this format's like not very easy to work with, so it might be easier to convert it into a hash map so that we have each node mapped to a list of that node's neighbors, because that way we can quickly do a O of 1 lookup on all of the map's neighbors instead of having to traverse through the entire array every single time we want to find what a node's neighbors are, So we're going to do that, and then for every single node, we are going to want to explore all of its neighbors, and basically you can do a DFS or a BFS, whatever you find easier. So we're going to also want to keep track of all of our visited nodes in a set, so that way if it's already in visited, we don't want to visit again, because then we're going to cause an infinite loop, like going back and forth between 1 and 2, so we don't want that to happen. So let's start out by initializing our map, and we're going to do integer with a list of integer, graph is new hash map, and then we're going to want to loop through our array here to fill out our hash map with each node and its neighbors. So we're going to start this out empty, and then for an I is 0, I is less than is connected dot length, I plus plus, and then if we don't have I in our graph already, then we're going to add, because this is the whatever node we're at, if we don't have that node in our graph already, we're going to add that. So put if absent, and then we're going to add that node with a empty list like that. So at 0, then we don't have 0 in our graph yet, so we're going to add 0 mapped to an empty list like that. And then we're going to do the same thing for j. Or we're going to start this at I plus 1, because basically we don't want any duplicates, because if we start j back at 0 again, then we're going to have duplicates where first we're going to compare from 0 to 0, and even though this is a 1, it doesn't really mean anything, because it's basically saying that this node is connected to itself, which we don't actually care about that, in terms of our provinces, so we don't really want to count that. And then same for here, at 0 1 or 1 0, these are both 1, but these mean the same thing, so we don't want to count it twice. So we're going to start j at I plus 1 just to avoid any duplicates. J is less than is connected at I dot length j plus plus, and we'll do the same thing for j. So basically here, since we start j at I plus 1, we're starting j at 1, so we can check, do we have 1 in our graph as a key yet? No, we don't, so we can add 1 and with a new empty array list like that. And another thing to keep in mind here is our array is 0 indexed while our example is 1 indexed, so just don't get confused about that, keep that in mind. Because 0 here technically means 1 here, 1 technically means 2, and then 2 technically means 3. So just add 1 from here or subtract 1 from here, whichever makes more sense to you. But just another thing to keep in mind. So then after that, we will want to check if that value is 1. So if is connected at I at j equals 1, then we're going to want to add that as a neighbor. So then graph.get I dot add j. And same thing for j. So get j dot add I. So if we check for 0 and 1, if that equals 1, and it does here, as we can see, right, in this line, then dot get I, so I is 0, so graph dot get 0 is going to be in this list, and then dot add j, and j is 1, so we add 1 here. And then same thing for this other one, so graph dot get j, well j is 1, so that's going to be this key. And then the list for this key, we're going to add I, and I is 0, so we add 0 here. And then as we can see, right, because remember 0 actually means 1 and 1 actually means 2, so then 1 and 2 are connected, as we can see here. So we're adding each of these as a neighbor to each other, which is accurate, so we do want that. So then when we loop through here again, then I becomes 1, and then j becomes 2, because j is I plus 1, remember? So then we will check if we have 1 already as a key, and we do, so we do nothing here. And then we check here if we have 2 as a key or not, and we don't, so we're going to add 2 with an empty list. And then if at I at j, so at 1 at 2 is 1, and it's not, it's 0 here, so we don't do anything, we just skip over this. And then at the next iteration, this is 2 and this is 3 because it's I plus 1. And then we just exit the loop because we don't have 3 in, we don't have an index 3 here, so we just exit the loop. So then this is our final graph up here, which if we look at this, then that is correct because we have 0, which is 1, connected to 1, which is actually 2, and then same thing here. So 2 is connected to 1, and then 3 is connected to nothing. So this is accurate. Okay, so now that we have our hash map set up, like mapping all of our nodes to all of their neighbors, then we'll want to do a DFS on each node and all of its neighbors. So we're going to start with the node 0, for example, and then we're going to check all of its neighbors, so 1, and then we're going to go to 1 and check all of its neighbors, which is 0, but since we've already seen 0, then we would skip that, and then we would move on, and then once we move on, we know it's like a new component, so we can start that process over again. So to do that, we want to keep track of the number of provinces, which will start at 0, and we'll want a set to keep track of all of our visited nodes. And then we will loop through our graph's key set, because these are all of the nodes. And if it's not already visited, then we will increase our provinces, and we will do a DFS on this node. So we'll pass in our node, we'll pass in our graph, and we'll pass in our visited set. And then at the very end, we're just going to return the number of provinces that we actually found. So basically because we'll also want a private method, private void DFS. And this is because so we're only gonna, we're gonna recursively call the neighbors, but only up here we are actually going through each node in the key, if that makes sense. So we're only gonna increase provinces out here, which is if we haven't already seen that neighbor before, so it's a new component. I don't know if that'll make sense, but maybe it'll make more sense when I start doing the DFS. But we're gonna pass in the node, we're gonna pass in the graph, so map integer list integer graph and set for visited. So first thing we want to check is if we've already visited this node before, then we will just exit because we don't want an infinite loop. So if we start at 0 and then we do a DFS on 1 and then we do a DFS, or we check 1's neighbors and we see 0 again, we've already seen 0, so we're just going to exit. We don't want to go back to 0's neighbors, which is 1, and then that's an infinite loop. You know what I mean? So we'll just return if we already seen it. If not, then we will add it to visited. So now we have seen it, and then we're going to and then we're going to loop through its neighbors. So for each neighbor in our graph's nodes list, so .get node, then we will do a DFS on the neighbor. So neighbor graph visited. And that should be it. Okay, so this one is a little bit more complicated than usual for the time and space complexity. So the time complexity, so like let's think about what we actually did here. So we first, and I'll pull this down so we can see better, but basically we looped through our is connected array n squared times, because like n by n, right? Because we had to visit every single one in here basically. Well, not exactly, but like n squared divided by 2 basically, which is still n squared, right? So that simplifies to n squared. And then down here, we're visiting each node in the key set, which is just O of n. And then we do a DFS on each neighbor, which is O of E basically, because it's like the total number of edges, like for each edge we're going once. But I think E still gets like the number of edges gets dominated by the n squared in this case, because like we're always going, like no matter what, we have to traverse this n squared times, as we can see by like the nested for loop, and the number of neighbors is like always going to be less than n squared, you know what I mean? So this will get simplified down to O of n squared, where n is the number of nodes in the graph. And our space complexity, so like let's think about what data structures we have here. So we have this graph, or hash map, I guess, which represents our graph. And in here we are storing each node, which is O of n, and each of the node's neighbors, or edges, I guess, either way, which is O of E. And then basically, so that's n plus E basically. And then down here, because like even though we're traversing through n squared times, we're actually only storing each n once. Like we're not storing n squared nodes. So it's still O of n for space, or n plus E, I guess. And then for our set here for visited, we are storing O of n because we're visiting each node one time. And we're not storing any of the edges in the set, just, well, like, I guess, but like it overlaps because like each edge is like technically also the node. Like, you know what I mean? Because we're visiting the node and its neighbors, but like they're the same nodes over again and we're not re-adding it, so it's still just O of n. And then yeah, I think that's it for data structures. So it just simplifies down to O of n plus E, where n is the number of nodes in the graph, E is number of edges in graph, because yeah, like here the E does not get dominated. Like worst, well, I guess, okay, so worst case, like every node is connected to every other node, and then like we would end up with like n plus E, because then we're storing every node and every other node like in the hash map, like, you know what I mean? But if not, like if it, like for example 2, like we would basically end up with a hash map that looks like 0 to nothing, 1 to nothing, and 2 to nothing, right? Like where 0 is 1, 1 is 2, and 2 is 3 again. And so this one we're actually just storing O of n because there's no edges to even store here. So like it just depends on like which case, because this would be like best case, and worst case is like if we had like 1 connected to 2 connected to 3 connected back to 1, so everything is connected back to each other, which like then in that case you would have like 1 2 0 2 and 0 1 like this, and that would be like n plus E, you know what I mean? Like technically this is also n plus E, but like this is more edges. But anyways, now I'm like kind of rambling, but I hope that made sense. If you found this helpful, please like and subscribe, and thank you for watching. Bye.